All right, guys. So unfortunately, for a variety of reasons, I'm probably going to have to cancel class this morning. So I'm just going to record a quick video, actually a couple quick videos that talks about some of the topics that we talked about last week, like the mean value theorem, and then also some of our new topics. So first I want to do a quick review of the mean value theorem. So remember we talked about the mean value theorem last week. Basically, the mean value theorem says if a function is continuous and differentiable on an interval, then there exists some c in between the endpoints of that interval. So notice that here we're looking at our function between a and b. Mean value theorem says there is a c somewhere between a and b, such that the slope of the tangent line at c, that's the blue line, is equal to the slope of the line between the endpoints. So if you notice, we've got two parallel lines there. That's what our mean value theorem says. Now, mean value theorem doesn't technically tell us what that c is, but we are often asked to calculate that c, and so we're going to go ahead and practice that. So I'm going to pause the video and put up a new problem, and we'll work it. Okay, so let's work this problem. If our function is a square root of 4x minus 3, determine if the mean value theorem applies on the interval 1 to 3, and if so, find the c guaranteed to exist by the theorem. So let's talk about the first part. Let's figure out if the MVT applies. So if the mean value theorem applies, our function, f of x, needs to be continuous and differentiable on the given interval. Well, let's think about this function. Square root of 4x minus 3 is a simple square root function that's been shifted. Okay, so if we think about a graph of this function, well, it doesn't exist anytime our argument, or what's under the square root, is equal to 0 or less. So 0 is okay, but anything less than 0 is not. However, I think if we do a little bit of testing, if I were to plug in 1 to this, I'd have 4 minus 3. 4 minus 3 is 7. Square root of 7 is okay. If I were to plug in 3, I'd have 4 times 3, which is 12. 12 minus 3 is 9. Okay, seems like we're okay inside of there. So it seems like all right, so let's take a look at this example. Our function is going to be 4x minus 3, and we're going to determine if the mean value theorem applies on the interval 1 to 3. If so, we're going to find the c guaranteed to exist by the theorem. All right, so remember that for the MVT to apply, we need our function to be continuous and differentiable on the given interval. Okay, all right. Well, let's think about this logically. This is a square root function, so it's actually not continuous everywhere like a polynomial would be, but it's not going to be continuous anytime we get negatives under the square root. Let's see, we're going to get negatives under the square root when we have things that are smaller than, let's see, this is going to be 0 when x is 3/4. So anything smaller than 3/4 is going to give us a problem. However, now we're between 1 and 3. So it seems like this is going to be nice and continuous and differentiable on our given interval. If we really want to double check, we can look at a quick graph of this. So I've got one up here I'm going to share. So here on Desmos, we can see a quick graph. Here's the square root of 4x minus 3 function. And if we're looking between 1 and 3 on that interval, that function sure looks nice and continuous. Okay, good deal. So the MVT does apply because our function is both continuous and differentiable on 1, 3. We need to state that, okay? So now that we know that it applies, let's try and do the second part. Let's try and figure out if we can find the c guaranteed to exist by the theorem. So remember, the theorem says we're going to have f prime of c equal to the slope of the line between the endpoints. So our endpoints are 1 and 3. So if we think about our function, we need to know what our function value is at 1 and what our function value is at 3. So when I plug 1 into my function, I get 4 times 1 minus 3. Well, 4 minus 3 is 1, so I get the square root of 1. So I have the point 1, 1 sitting on my function. If I plug in our other endpoint, 3. We'll have 4 times 3 minus 3. 12 minus 3 is 9. Square root of 9 is 3. So I'll have the point 3, 3. Okay, so the endpoints of my function are 1, 1, and 3, 3. But I know how to calculate a slope between those endpoints. The slope of the line between 3, 3, and 1, 1 will look like 3 minus 1, y2 minus y1 over x2 minus x1, which is 2 over 2. Oops, 2 over 2, which is 1. So the slope, in terms of our function, f of b minus f of a over b minus a, this is what we actually explicitly state in the mean value theorem, the slope between the endpoints is 1. So what we need to find is we need to determine where is the derivative of this function equal to 1. So that's kind of what our question has boiled down to. Let's see if we can figure that out. Well, it seems like we're going to need to take the derivative. So I'm going to take the derivative of our function. Remember that this is really 4x minus 3 to the 1. Goodness, I can't write half. So using chain rule, my derivative will be 1/2 times 4x minus 3. 1/2 minus 1 is negative 1/2. All right, times derivative of the inside is 4. Now because we're going to be using this derivative, I'm going to go ahead and simplify. Okay, 1/2 times 4 is just 2. When I have a negative power, I can move that into the denominator. So I can think of this as 4x minus 3 to the 1/2, or if you want, I could think of this as 2 over the square root of 4x minus 3. Okay, there's our derivative. Now remember, we wanted to know where is this derivative, for what value of x is this derivative equal to the slope of the line between the endpoints of our function, which we calculated to be 1. So now we're trying to solve this. All right, here comes some algebra. First thing I'm going to do is I'm going to multiply both sides of this by the square root of 4x minus 3. That's going to clear my denominator here, leaving me with 2 on this side equals 1 times the square root of 4x minus 3. Okay, so now if I'm trying to solve this for x, I'm going to square both sides of this equation to get rid of that square root. 2 squared is 4. Square root and squared cancel, leaving me 4x minus 3. And now we've got something we can solve. Adding 3 to both sides, I get 7 equals 4x, or x equals 7/4. So c equals 7/4, meaning the slope of the tangent line at 7/4, which is between our interval 1 and 3, should be equal to 1, the slope of the line between the endpoints. Now I'm going to real quick model that on a graph using Desmos, just so we can kind of see what that looks like. Okay, so remember that the point we found was 7/4, so let's look at what that looks like on a graph. So hopefully you can see Desmos here. So we've got our function. The green line is our f of x equals 4x minus 3 function, and then I've labeled our 2 endpoints, 1, 1, and 3, 3. So that's our interval from 1 to 3. Okay, now I'm going to go ahead and put in, there's the line between those endpoints. So there's the straight line between those endpoints. Notice that that line sure does have slope, rise over run, of 1. Okay, so now when we did our calculation, we said that c, which should be between 1 and 3, and it is, should be 7/4. So there's our little c, 7/4. And then let's go ahead and plot that on our graph. So there it is on our graph. Turns out that's the point 7/4, 2. Okay, now we want to show that the slope of the tangent line there is the same as the slope of that purple line, the line connecting our endpoints. So here I've gone ahead and put in our tangent line. So here's our tangent line going through that red point. That's c, f of c, or in this case, 7/4, 2. And what do you notice about those two lines? Well, they're parallel, meaning they have the same slope. And we can even explicitly check that because the slope of that red line, does it look like it's 1? Well, it's not a very nice line, but it sure looks like it's going up 1 over 1 every time. So that just confirms that we found the correct C for our mean value theorem.